We're going to start our discussion of vector and matrix algebra by introducing our notation. First of all, how do we show a real number? A real number we can show with a lowercase letter a, for example. A complex number we're going to show with an uppercase A with a line underneath. For a vector, we're going to use an arrow on top. So this is our vector A. Now, if we want to show a unit vector, which is the ith unit vector or ith basis vector, we're going to show it with unit vectors with e sub I, and we will put a hat on top to show that it's a unit vector. Now the ith component of a vector A, we're going to show with a sub I, and for a matrix M, we're going to use these square brackets. All right. And if you want to refer to the elements of this matrix, the ith row and jth column matrix element, we're going to show it with M sub I j. So this means the first index is for the row, the second index is for the column. So this is ith row, jth column of matrix M. So this is corresponding to this matrix element. So just to summarize, we have a real number A, and then we use A with a line underneath to show it's a complex number, A with an arrow on top to show that it's a vector. The ith basis vector, which is a unit vector, is shown with e sub I hat. The ith component of this vector A is shown as a sub I. For a matrix M, we use square brackets, and we refer to the ith row jth column element of the matrix as M sub I j. All right. So with that, we can represent a three-dimensional vector A as its components a sub x ex hat plus a sub y ey hat plus a sub z ez hat. So this is written in terms of its components, x component, y component, and z component. So we have the x component is the first component, a sub 1, y component is a sub 2, and z component is a sub 3. These are the, because I'm using Cartesian coordinates here, are the Cartesian components of our vector A. And now these unit vectors, e sub x hat, the basis vectors, are basically I hat, which is the first basis vector in the Cartesian coordinate system. E sub y hat is what we call j hat, which is the second unit vector, basis vector, and e sub z hat is k hat, which is the third basis vector for our three-dimensional space using the Cartesian coordinates. So these are the basis and unit vectors in the Cartesian coordinate system. So we can show them here. For the x-axis, we have e1 hat or ex hat. For the y-axis, we have e2 hat, which is ey hat. And for the z-axis, we have e3 hat or ez hat, which is k hat. So these are unit vectors. And we know that their magnitudes are shown with this absolute value here, E1 hat magnitude is equal to E2 hat magnitude is equal to E3 hat magnitude, and this is 1 because they're unit vectors and they're orthonormal to each other, which means that if I consider the angle between these two vectors, EI hat and EJ hat, that angle is 90 degrees, which means their dot product will be 0 when I is not equal to J. If I is equal to J, it's going to be equal to 1 because they're also unit vectors. Okay, so using the subscript notation, we can write the vector A as its component A1, E1 hat, plus its second component A2, E2 hat, and its third component A3, E3 hat. Or you can notice here, this vector A can be decomposed into its components sum over I, index I, A sub I, E sub I hat. So it can be written in terms of its components as a summation over I as A sub I, E sub I hat. Now, what we show here equivalently can be written using the Einstein summation notation. So what's the Einstein summation notation? So using Einstein's summation notation, we can write this as vector A is equal to AI EI hat, which means it's the summation over I AI EI hat. So what does that mean? You can see here, if I have two of the same subscripts, I, A sub I and E sub I hat, a summation here is implied whenever a subscript is repeated. As you can see here, it's repeated, so that implies this means we have a summation over this index I. All right, so we were able to write a three-dimensional vector in terms of the unit vectors which are orthonormal in the Cartesian coordinate system, and we can also rewrite this using the subscript notation by replacing x with 1, y with 2, and z with 3, which means it's sum over I, AI, EI hat. And using the Einstein summation notation, we notice that whenever a subscript is repeated twice, it means there is a summation. So that this is to say vector A is AI EI hat, which means it's sum over I AI EI hat. So this summation is implied. Okay, so when we have two vectors added together, this is vector A plus vector B, and this is basically how I write the sum of the two vectors using vector notation. This equation implies, in terms of the components of these vectors, the first component of the resultant vector R1 is the first component of the vector A plus the first component of the vector B. R2 is A2, A sub 2 plus B sub 2, and R3 is A sub 3 plus B sub 3. Okay, so equivalently, we can write this using subscript notation. R sub I is A sub I plus B sub I, where I takes values 1, 2, and 3. So this we were able to write using subscript notation. All right, so that's our equivalent equation using the subscript notation, or using the vector notation, we can write it as the sum of these two vectors in this way. Now if I have a matrix, let's say that I have this matrix M, and remember I use square brackets to show the matrices. It has elements M11, first row, first column, M12, first row, second column, all the way up to M1C for the seed column. Then I have second row M21, second row, second column M22, and then I have second row seed column M2C, and MR1, rth row first column, MR2, rth row second column, etc. And then I have M sub RC, rth row seed column. So here M sub ij is the ith row jth column element of this, and you can see that a matrix M is a two-dimensional array of numbers. Okay. All right, so we have talked about our notation, and we have talked about how to represent a vector in terms of its components, both using this vector notation or using the subscript notation as sum over I, AI, EI hat, which translates to, in Einstein summation notation, AI, EI hat only without the summation, because the summation is already implied by the presence of these repeated subscripts. And we have seen that these unit vectors, are basis vectors in the Cartesian coordinate system, are orthonormal vectors and they're unit vectors. And when we write vector addition, we can either use vector notation, or we can write it in terms of the components using the subscript notation. So R sub I, ith component of the resultant vector, is the sum of the ith component of the first vector plus the ith component of the second vector. For 3 dimensions, this would be, I can take values 1, 2, 3. And a matrix is represented as a two-dimensional array of numbers with the ith row jth column element being M sub ij. So these elements form this two-dimensional array starting from M11, M12, M1c, but for the seed column. And then we have rth row first column MR1, rth row second column MR2, rth row seed column MRC. So this is our matrix representation.